What is a complex number? We're going to try to figure that out today. So in this video, we're going to be looking at what a complex number is, how they came about, and how we might view them compared to real numbers. So if you're studying in the New Zealand curriculum, NCEA, complex numbers, this video will be perfect for you. So let's get into it. What is a complex number? Well, the story begins in around about the year 1500, not 500, 1500, and people were starting to explore different problems, and this particular problem popped up quite a lot. Now, it wasn't exactly this problem, it was usually a bigger problem that engineers were trying to solve, and this was like a stepping stone in that problem, and it kept popping up, and it proved to be a problem. So if you look at this problem, x squared plus 1 is equal to 0. There are some immediate issues. The reason being is that when we square a number, no matter what number that is, it becomes positive. So for example, if you're squaring -2, the answer becomes 4, positive 4. So any negative when you square it, it's positive. Any positive when you square it, it's positive. And if we're adding 1 onto that result and trying to get 0, we have some real issues. We would need this to be -1. -1 plus 1 would be 0. However, there is no possible way that x squared can become -1. Now this, as I said, kept popping up as a stepping stone in a bigger problem that engineers knew there should be a solution to. They were working with things that in the real world they kind of knew what was happening. They were trying to get the maths going with it, and they couldn't quite get it to work because of this. However, they knew that there was a solution. They knew that there should be some way to solve this in order to get to what they needed to get to. And so they started to play with the idea of how could we kind of find a loophole around this. So if we just try and solve this with the algebra that we do know, so I'm going to -1 over to this side and end up with -1 and still have my x squared here. And now I'm going to take the square root of both sides. X is equal to technically plus or minus. I'm just going to look at the positive version of this. The square root of -1. Now, if you type this into your calculator, the square root of -1, we are going to end up with some real issues. It just tells me error, math error. You might be getting a different message, but there's no solution, as we talked about earlier. Now, this leads us directly to what an imaginary number is, which is part of our complex numbers. So, it turns out that this doesn't exist. There's no way for this to happen. And one guy a long time ago, like I said, in the year 1500, he just said, what if there was? What if this did exist? At the moment, it doesn't. There's nothing for this. It's an error. He wondered, what if it could exist? And he imagined that there was an answer to this. And that leads us to imaginary numbers. So imaginary numbers is just that. He's going to say, let this square root of -1, which we just had on that last page, let's call that something. Let's call it an imaginary number. We're going to call it I. So this is the introduction to complex numbers. We've introduced this new idea that this does become something, and we're going to call it I. Now, naturally from here we can square both sides, and we end up with I squared is equal to -1. Now, we're going to be using these a lot throughout the topic of complex numbers. This one, not so much. This will pop up a little bit, but this one here we will be using quite a lot, and we'll be using this letter I quite a lot, an imaginary number. Now, we've just introduced a new number. How does it relate? How do these new imaginary numbers relate to the real numbers that we already know? We have some problems. The first problem is we have a number line. This is our number line. We have 0 in the middle. We're going up 1, 2. These are called our real numbers. And it is said that the real numbers on the number line, the word we use is dense, which means that there's no space to put any new numbers that aren't on it. So we do have half. It would sit here. We'd have something like 0.1 over here. We could have 3/4. All of our fractions, all of our decimals, they all fit on our real number line. We even have square root symbols that have infinite decimals. They fit on here as well. We have pi, which would be 3.14 up here somewhere. There's no space to put this new invented imaginary number that we have invented. And so a clever person realized that we could actually now delve into the 2 dimensions. If we add another axis, and we're pretty familiar with having an axis like this, we're going to call this axis our imaginary axes. And now we have a place to put complex numbers, imaginary numbers for starters. So we're going to call this I, or 1i, 2i, 3i. We can go down, negative 1i, negative 2i, negative 3i. We can actually have 0.5i in here somewhere. We could have all of our fractional and all of our decimal versions of this imaginary number. We've let the first one just be the square root of negative 1, but we could double it. We could have 2i as 2 lots of the square root of negative 1. We could have 5i as 5 lots of it. That is fine. So they are going to go now on our imaginary axes and our real axes. And now we have a place to imagine the mixture or the combination of our real numbers and our imaginary numbers. So let's go a little bit further and look at what we call a complex number. So a complex number, we use the symbol capital C with this little line to denote the set of all complex numbers. I might make a video talking about all the different sets that we have. But complex numbers, and usually in algebra, when we're working through complex numbers, we use the letter Z to represent a complex number. Now, a complex number, we've just talked about imaginary numbers. A complex number is the mixture of real numbers and imaginary numbers in any combination that we want. So we're going to say Z is equal to x plus iy. And just before we were talking about our axes, this is our real axes, this is our imaginary axes. So everywhere on this grid is going to be the space for us to think about complex numbers. Complex numbers are the addition of some real number and some imaginary number. So in algebra, all the way up until this point, we've typically used the letter x to represent just a random number. And now we use Z to represent a random complex number, not to get confused, where X will be the random real part and Y will be the random imaginary part. We're going to merge these together to create a topic called complex numbers. Now, the first thing we really want to do, and it's very basic, we'll be pretty familiar with it, is how do we now put these on our axes? So let's look at some examples real quick. This should be pretty straightforward, hopefully. If you know how to grid on an XY axis, this is fine. Actually, just real quick before I take it back, we call this new axis, this is called the Cartesian plane. Now, basically, that was just the name of the guy that invented it. That's why we called it. It's nothing important about the actual word Cartesian. It's to pay tribute to the people that invented this stuff. So let's look at some examples. We want to plot these complex numbers on the Cartesian plane. Here's my first one. So it's 3 plus 2i. We've just invented these imaginary numbers. Don't get too bogged down by the idea that I is the square root of negative 1. We're just going to accept that these i's are a new type of number. We actually don't really know what they are because obviously they are the square root of negative 1 that doesn't exist. But we're just going to imagine that now they kind of sit on this axis here. We're not 100% sure how they work just yet, but right now we're just going to say we've introduced this new set of numbers, these imaginary numbers. We've imagined that they exist. They're going to sit up here on this axis here, and now we can start to view complex numbers sitting somewhere in this plane. So 3 plus 2i, it's very, very similar to if we're plotting a coordinate. We're going 3 in the real direction, 1, 2, 3, and we're going up 2 in the imaginary position. So this is going to be that complex number 1. This being the 3 and this being the 2i. And so a complex number can sit on this point right here. Second one, excuse me for a second, my light just turned off. I don't know how to fix this problem with the light going off halfway through my video, but we'll figure it out at some point. All right, next one. Negative 2 minus I, pretty straightforward. Let's go a bit quicker. Negative 2 is going to be here. Negative 2. Negative I is going to be here. So number 2 is going to sit right there. Minus 2 in the real and down 1 in the I. Third one. They've tried to confuse me a little bit here. They've put the I at the front and the minus 1 next. That's my real part. So I've gone back 1 and up 3i, and so 1, 2, 3. This will be my third complex number. Negative 1 in my real direction, 3i in my imaginary direction. And the last one, you'll notice there's no real part on this. This complex number is actually purely imaginary. There is no real part. It's purely imaginary. It's one of my imaginary numbers. We can still plot that here. It just has no real component. It's only imaginary. So we're going up 3i, and there it will be right there. If I was right in the middle here, right in the very, very center, this is a very unique complex number. It is 0 plus 0i, called the origin. All right, that was our very short introduction into complex numbers. Just so you know kind of where they're used and why we even study them. So like I said, in the year 1500, people started exploring this stuff. The first applications came in electrical engineering, where we could use these to help us understand alternating currents, circuits in particular with alternating currents. It then got used in some quantum mechanics, where we start to delve into the extremely microscopic stuff, and it actually figured out how to kind of model the behavior of particles. We use complex numbers to help us do that. And then lastly, in signal processing, these will help to represent the wave functions that we see. So there are some very, very real practical applications of complex numbers. And it all came because one person was brave enough to say, hey, let's just imagine. And people did not like him for imagining that there was a solution to the square root of -1. That was pretty widely understood that there was no solution to that. And he stepped out and said, well, let's just imagine that there would. He followed through. We're going to look at how these can relate, how we can work with these complex numbers, and how they use them to actually apply to these real world situations. So hopefully this video was useful. We'll catch you guys later. Thanks for watching. See you later.